functions that are integrating over non-rectangular regions, over general regions. So double integrals over general regions. So initially, what we do in the theory is we make it into a rectangular, into integrating over a rectangular region. So let's say, for example, that, okay, let me say this is the X and the Y axis, right? And let's say that you have this weird shaped region like this. Okay, and we'll say this is R. So what you would do, no, that's not R. What am I thinking? That is D. Okay. So what you do is you find a rectangular region that encloses that. So any rectangular region that encloses that. And then you come up with this new function here, which you call capital F. So you have the small f right here, f of x, y. Capital F will be small f if x is in here, and then it will just be 0 if it's not in. And so then you're just integrating over, you integrate over this rectangular region, just integrate this new function. Okay, so that's in general how you do it in theory. But it really doesn't come to that in practice. I'm just saying that's the technique for like making all this theoretical stuff work out and all the rigor and everything. That's the route that you go to prove theorems and things, which some mathematicians like to do. But in reality, from your point of view at this point, there's a few situations there's a few things that there's a couple techniques that you do. Okay, and one of them is if you have a region like this. Okay, and now let me draw a couple of examples of what this would look like. So you either have something like, and again, your X and Y axes are going to be here. So you could have something like this. And this top one would be G2 of X, and the bottom one would be G1 of X. And let's say that this right here is your region D. So this right here inside is your D. Okay, and then this right here, this point here would be A, and this point here would be B. Okay, so that's one situation where this comes up. So notice that Y, your region is defined this way, that Y is between G1 and G2, and X is between A and B. Okay, so this would be like, you want the region that's enclosed by these two curves. That's below this curve and above that one. And there's your region D right in the middle. Okay, so that would be one situation where that would come up. Another situation would be something like this, where we just have G2 of X up here, and then G1 of X down here, and then A is just some point here and B is some other point there, and your region is defined like this. Okay, so these A and the B, I'm just pointing out, saying that the A and the B don't necessarily have to be like where these two curves intersect or anything. It could just be, okay, you only want to know what this area is in between. Okay, so if you have that, then if you have this situation here, if you can describe your region like this, then here's your integral. okay? You're integrating this function at little f over either of these regions. Then you're going to integrate in y first, and you're going to go from g1 of x to g2 of x. And you integrate this function in y. And then after you integrate that, then you're going to, if you find an antiderivative, you're going to plug the top one in and then subtract and plug the bottom one in. And notice that when you do that, that's going to get rid of all your y's. All your y's are going to be gone. You only have x's in your equation. And then you integrate an x from a to b, from a to b, a to b. And then there you go. So that would be that's how that works. Okay, this next one. This is right here. If you have this kind of situation, so here you have h, you have x's between h of h1 of x and, hold on a second. I think I made a mistake there. Yeah, I made a mistake. Okay, so this should be h1 of y, and this should be h2 of y. Okay, so here what's happening here is your h2, okay, so you have x equals h2 of y over here. And by the way, this is y equals that, and that's y equals that. And then over here you have x equals h1 of y. Okay, and then you have from C to D. So your region looks like this. And so you're going to integrate, so if you can express it this way, then you're going to integrate this first with respect to x. So from h1 of x, of y to h2 of y. These should be y's again. And you're integrating with respect to x. So you integrate this with respect to x, then you plug in h2 of y, subtract and plug in h1 of y. And that, again, when you do that, that's just going to give you something in terms of only y. And then you integrate that in y, and then you're done from C to D. Okay, so those are the two main tools. Now, sometimes you have to be intuitive, and I'll show you some examples later. But not all regions are going to be able to be written in one of these two ways. I think they call this type 1 and that type 2. But not all regions are going to be able to be expressed in this way, in one of these ways. But what you can do is you can split regions into multiple parts and integrate each. Okay, so if you want to integrate, if you have a region that doesn't split up into these, maybe you can split it up into subregions where all the subregions, the union of the subregions is equal to the overall region. And then integrate over, but then each of the subregions you can split up into one of these ways, and then integrate over each of those, and then add all the integrals up. Okay, so that's another technique that you can do. Okay, so let's get to the exercises. So when you integrate these kind of things, the first limits of integration are going to typically have the other variable in there. You're going to have expressions involving this outer variable. Okay, so let's do this one. And here again, you're just going to focus on just this part here. So that one is going to be set aside for a little bit. Okay, so if I integrate with respect to t, if I integrate this with respect to t, what do I get? So this is dt ds right here, right? Okay, what's the integral of cosine of s to the 9th dt? Just with respect to t, so that means that s is like a constant. So that means I'm just going to get a t come out. Okay, so this had no effect on the, cosine. That's just like, well, this whole thing just treated like a constant at this point. Okay, and then another thing that I like to do, which you've probably seen me like to do, is make sure that that's our t, because it's come from the dt, so it's t equals, so these limits are in t. T equals 0 to t equals 8. Okay, if we plug the upper limit in, we get s to the 8th. Subtract, plug the lower limit in, and that's going to be 0. Okay, so we have the integral from 0 to 1 of s to the 8th cosine of s to the 9th. Oh, I like that. What's the integral of that? What's the integral? What's that?
Don't you use Voodoo to solve this?
We get rid of. Wait, what's the integral of cosine?
Sine?
Yes. Okay, if we take the derivative of this.
9s to the 8.
Yeah, we'll have a 9.
Cancels out the other s to the 8th.
So we just need a 1/9 to counter, right? Okay, now you plug in a 1. Sine of 1, that's awkward. Subtract and plug in a 0, and that's 0, right? So 1/9 sine of 1. Oh, that's weird. Really, is that really the answer? Yeah, it is the answer. Okay, so number 2, we're supposed to evaluate this integral. And here they've written it as what they call a type 2 interval, type 2 integral. So that means, so here we have y over x squared plus 1. That means that because the y has x's in the limit, that's going to go first, like that. And dy. And then we'll do dx, we're going from 0 to 9, like that. Okay, so you're going to integrate with respect to y first, this whole thing. And that's just going to give you y squared over 2, right? Well, you'll have this extra plus 1 there still, right? And that's going to go from y equals 0 up to y equals the square root of x. And then you're going to integrate with respect to x later. Okay, if you plug in the square root of x for y, then you just get x. Whoa. And then subtract, if you plug a 0 in for y, you get 0, so that's gone. Okay, so we just have that integral there. Okay, great. What's this integral going to be? I'll pull this 1/2 out here.
It's gonna be 1 over x squared plus 1. Yeah. Wait.
Wait, the integral.
Integral.
Think integral. So you have an x right there. You've got x squared right there. Which are you more afraid of, the x up here or the x squared down there? Which is more scary if it's in your closet?
Isn't it gonna be like the bottom one is gonna be like 2x and then divided, so the top one, oh, ln. Doesn't see that.
Okay, what's the derivative of log of x squared plus 1? It'll be 1 over that times 2x, right? So we'll have another 2. We'll have a 2x come out there, and there's your x. This will take care of the 2. This 1/2 will take care of the 2. Okay, so from 0 to 9. Okay, so that's going to be 1/4 log of, you put a 9 in here, you get 81. Log of 82, really? That's weird. Minus 1/4 log of, if you put a 0 in, then that's going to be log of 1, which is 0. So I'll try that one right there. 1/4 log of 82. Okay, great. So that's the answer right there. 1/4 log of 82. We have these where the key is that g of x, that y is bounded by g1 of x and g2 of x. So you're something like this. Okay, another one is like this. Now, one thing, it's just like with the other class, that if you see something like this, then what you want to do, it's just like with previous experiences with this sort of stuff. You've seen this kind of stuff before. So like, for example, here, if you see that you've got this kind of situation and you're back between here and here, and you have this x's between these values, then what you want to do is, if this equation is y equals f of x, y equals something in terms of x, then you want to flip it around and solve for the x. So you have x equals h2 of y in this one as well. Okay, so that's basic idea there. We're just reviewing a little bit. Okay, so let's look at this exercise here. Here we have, you want to integrate this over this region, and the vertices are, let me just draw a picture of that. So 0, 1 is right there. 1, 2 is up here, and then 4, 1 is over here. Okay, so this is the region. This is the triangle. This is the region that you want to integrate over. Okay. Okay, so if we're looking at top and bottom, then you have one thing up to here, and then from here over you got something else, right? So if we look at it vertically like this, then you have something here, and then you have something else over here, right? If you're looking at this minus this. So this function is, in other words, this function here that determines this upper bound is different than this function here. So you could split it up into 2 integrals that way, if you wanted to do it that way. Or the other option is you could go this way, and going horizontally, there's this side, and there's this one right here. Okay, so that means that we can set it up as a type 2, what they call type 2 integral. Okay, so what we have to do is figure out what the equations of these are. So essentially, the question is, what is the equation of this line right here? Okay, so do you guys know the equation of that line? Well, we can find it in terms of y.
Right, it would be y equals to y equals to x plus 1.
Yes, good. The slope is one because from here to here you're going up 1 as you go across 1, right? And then the intercept is 1 because it's right there. That's the intercept. Okay, so that's that one right there. So that one, when we flip it around, we get x equals y minus 1. So that will be our h1 of x. Okay, so when we set the integral up, our lower limit's going to be y minus 1. Okay. Wait, we're going to dx first, and then dy. Okay, and then our upper limit, we'll get it from here. Okay. So that brings us to the other line. So this one right here. And yellow's not a good color. I just figured that out. How about this one? Okay, so let's see here. Okay, so we're looking at the equation of that line there. What does the slope look like?
Negative something. Negative 2.
Let's see, from here to here,
Oh, it's
it goes down 1, right? And across by how many?
8. Well, 3 or 4.
From 1 to 4 is how
3.
many? It's 3, right? Okay, so negative 1/3 x plus b. I don't want to figure that. I don't want to try to figure out what that is. Then you can plug in one of these points, say maybe 1, 2. We'll plug in that point. Whoa, that's 7/3. Okay, so then that means that y equals to negative 1/3 x plus 7/3. Okay, if we multiply both sides by 3, we get 3y equals negative x plus 7. This guy go over there. And we have x equals negative 3y plus 7. So that would be the upper limit. And then the x's are going to go from, no, then the y is going to go from 1 to 2. Okay, so y goes from 1 to 2. So there's no x's in this expression right here. It's just a y squared. So what that means is when you take the integral, it's going to be just an x, and then you take the upper minus the lower. So it's going to be, you're going to end up with this, the upper one minus the lower one. Okay. So let's say here, this is 9y squared times negative 3y minus y, that's negative 4y plus 8. Get 36. Right. Negative 36 y cubed plus 72y squared. Where's the fourth? Okay, so I'm just integrating this, and then this one is dang, what's 72 divided by 3? $24. Okay, so plus 24. That's weird. Y cubed. Evaluate from 1 to 2. Oh my goodness. Okay, so that's okay, so I got 48, but that's not right. Oh, I forgot the lower limit. Okay, so that's just the upper limit. So that's going to be, let's see, 24 minus 9 is 15. Okay, so yeah, there we go. The answer is 33. Okay, any questions on that one? Yeah, let's go on to the next one, number 4. Find the volume of the solid that's under the surface is equals 1 plus x squared y squared, and above the region enclosed by these curves right here. Okay, so let's take a look at what these are first. Try to graph these. Okay, so we know that the first one, hold on a second. So we know that the first one is a parabola that opens up to the right, right? So it opens up like that. And the second one is just this line right here, x equals 4. And where do these intersect? What's the y value where these intersect?
Two.
Yes, 2. And then also here, -2, right?
Yeah.
Okay, great. So This right here is our region. And what you're going to, so you're trying to find what's underneath this surface. Now, for every single point in here, this is greater than 0. Okay, so really the object is something is in the three space right here. Okay, whereas this looks like this is just this parabola right here coming out. But really the region's kind of up here, you know. That's kind of hard for me to draw there, but the region's up here. It's something above this, and then so you're just looking at the volume of the solid. Okay, so that means that you can just integrate this function here over the region D. Okay, so anybody want to take a crack at what these limits of integration should be? Right here, these limits of integration on the first one, or should it be X? Should we integrate X first or Y first?
I'd say X first. If it was X, it'd be 0 to 4. And if it was Y, it'd be -2 to 2. Right? Or wrong?
That's if it were a rectangle. So the first integral, so what you want to do with the first integral should be in the variables here. It shouldn't be numbers, the first integral. Unless you have a rectangle, and if you have a rectangle, then it's going to be numbers. But since we don't have a rectangle, then the first limit should not be numbers. Or maybe one of them could be a number, but it shouldn't both be numbers unless it's a rectangle. And in that case, you have everything's numbers. And then the second integral has to be numbers, only numbers. The last integral always has to be numbers. So, so what do you think? What should these numbers be? Or what should these expressions be here, and here? So the thing is, yeah, go ahead.
I'm still thinking about it.
Okay. Okay, so there's two options. Let me just show you. There's actually two options for this one. One of them, the most natural one, would be to integrate in X first, and then Y. Okay, and then with this one, you're looking at a horizontal slice like this. Okay, and then this side of it is X equals Y squared. Okay, so the lower is going to be Y squared. And then this side is 4, so that upper is 4. And then Y goes from -2 to 2. Okay, the other option, mathematicians probably would be not as common to choose this one. It would be to look at a horizontal line, like a vertical line like this, right? Vertical segment here. And the Y goes from down here to up here. Now, if you take this X equals Y squared and you solve for Y, you get plus or minus the square root of X. So this bottom one is -√X. So that would go from -√X up to √X, up to +√X. And then X's would go from 0 to 4. Okay, so each value of x here represents, between 0 and 4, each value represents a horizontal, I mean a vertical line segment or strip. Over here, each value of y from -2 to 2 represents a horizontal strip. Okay, and then this is probably better. This is probably easier because if you do this one, then you're having to deal with square roots here. Okay, so whereas this one right here looks like, I think you're good. I think this is not bad. So let's just do it this way. Okay, another thing that you can, if you realize that the nature of this, well, I better just leave it alone. You can go, this outer one, you can actually go 0 to 2 and double it instead of going from -2 to 2. That's what I was going to say. Okay, so take the integral with respect to x, you're going to get x plus x cubed y squared over 3. And that goes from y squared to 4. And that's x equals y squared to x equals 4. So you're going to keep, so it's a good idea to keep track of what these are. These are, since you're integrating in x, this is x equals that, x equals y squared, x equals 4. And that way you know that it's substituting for the x, not for the y. Okay, so you put a 4 in, you get 4 plus 64 y squared over 3 minus, and then you put a y squared in, y squared minus, and you put a y squared there, that's going to be y to the 6th, 7, 8. Whoa. dy. Whoa. These two combine to give you 61/3 y squared. Okay, but let's continue. Okay, so this is, you integrate here, that's 4y plus 61y cubed over 9 minus y to the 9th over 27, really? Now, if you double it, let's just double it and go from 0 to 2. So putting a 2 in, you get 8 plus 61 times 8 over 9 minus 2 to the 9th over 27, really? Wow. Okay, let's see what that is. Okay, so 23/36 over 27 is what I got. And that's the answer to that one. Okay, so notice that here, we could have done it this way and come up with a different, and the work would be different, right? But in the end, we'd come up with the same answer if we did it correctly. So this has all these square roots. And so that's going to be kind of nasty to do. But in the end, we should get the same answer.
Brother Hurst.
And yeah.
How do we, like,
decide which one to use first? Like, do we work out the ty or tx, or we can?
You go with whichever looks easier.
Okay.
They both, if you can work them, they both are gonna give you the same answer if you do it correctly. So you just want to go with which one's ever is easier, and one of them might be nearly impossible
Wow.
to do. So, like for example, if let's suppose that this one right here, if we tried to do this integral, that would be impossible. Okay, but then again, it actually wouldn't be impossible, because one way that we could do this integral is we could look at it as, we could set it back up at the picture and reverse the order of integration and go, so like let's say that you're given this one right here. You can set this back up like that and say, okay, this one came from this situation, right? And integrating that thing over here. So you could set it back up like that and then go set this integral up, do that one, and this is the answer to that one. Okay, so like if this is integral 2 and we wanted to do this one, then we could set it up as integral 1 instead by just going back to here and then getting to that. So this is one way that we could find this kind of an integral here. But this is just for these specific limits. So it might have things that are impossible to integrate. It might have things that are impossible to integrate. But in this particular situation, it can be integrated because we have particular values right here that allows us to go this route. And so let's take a look at number 5, find the volume of the given solid. So it's bounded by z equals x, y equals x, x plus y equals 9, and z equals 0. Okay, so what you want to do here is, first of all, we're going to take a look at just these two right here, because those involve only x and y. The other ones involve z. Okay, so we're just going to look at those two right there, and then in the xy plane. So this is y equals x is right here. And then we have x plus y equals 9. X plus y. Wait, what is this? So that would be, so this one would be y equals negative x plus 9. So that would be, whoa.
So it'd be negative coming down from the 9. Yeah.
Okay, so hold on. Need more space here. Okay. So there's 9, and it's going to come down like that, right? And that's going to hit 9 over here too. Then you have y equals x, and that's going to be right here, going up like that. Let's see, where do these two intersect? That's probably an important point right there. Where do those intersect? If we add those two together, we get 2y equals 9. So you get y equals, 4.5. Or 9 halves, 9 halves. Okay, that's where they intersect. Okay. Z equals 0 would be like the xy plane, right? And then y equals, no, z equals x would intersect the x-axis, because z is 0. Wait a minute, no. It intersect the, I'm sorry, it intersect the y-axis. Okay, so let me see if I can give you an idea of what this looks like. Or actually, wait, no, that's the z. Okay, so this one right here would be this line coming out like that. And then this right here would be a line coming out there, like that, and right in there. And z equals x. That's going to go through there, but then it's going to, because x is 0, so z will be 0 right here. But then as x increases in value, here's x equal to 4.5. It's going to be up here. Okay, so you've got some kind of, it's like a wedge, is what it is, a wedge. And basically, we're going to integrate over this region here. And at each point in this region, the height of the wedge is this one. So we're integrating x. Okay, so does that make sense? So you have this wedge that starts at 0 on the y-axis and then comes out like right here. And this is 4.5. And this is, height's going to be 4.5 as well. Okay. So essentially, we want to just integrate over this region. And we know that this line right here is y equals negative x plus 9. We also know that this line right here is y equals x. And we know that this, of course, is this boundary here is x equals 0. X and y both equal to 0. No, x equals 0. But this is just the xy plane. Okay, so let me point out here, it's important to remember this is a three-dimensional object right here, and we're trying to find the volume of a solid. However, with just this information here, this gives us the height of the solid at any point. And so we're integrating over a region in the xy plane. We're integrating over a region in the xy plane. Okay, so which should we go first, dx or dy?
Let's go dx.
Okay, let me tell you how you can tell.
Yeah.
Okay, so the dy is going to be easier. Dx could be done, but dy is going to be easier. Let me tell you why. Here, if you look at vertical strips, okay, look at vertical strips and look at horizontal strips. Okay, which one is more clear? So if you got horizontal strips, the left side is 0, right? The right side is this. But then if you're up here, the right side is this one, right? So that changes. Okay, so that means that if you do x first, then you'll have to have two integrals. Okay? And the other thing you'll have to do is you'll have to solve these equations for x, if you do x first. Okay, so if you do vertical strips, then here's your upper limit, it's y equals this, and the lower limit's y equals x. So you have clear throughout the whole region. These are the boundaries throughout the whole region. So you'll just have one integral. And they're already solved for y. So, so one way you can tell is the vertical or horizontal lines, which one gives you a clear shot. The other way is that these are solved for y. This is solved for y. Y equals. This is y equals. Okay? So that means that the lower limit's going to be, with this lower one is y equals x. So the lower limit will be x. Okay? You could also think of it as being y equals x. Okay, which I tell you, you should think of that later on. And the upper limit's going to be negative x plus 9. Okay, then you have then dx. Okay, what's the limits on the dx? What are limits on x now?
On x, isn't it 0 to 9?
Okay, 0 is right here, but then what's this?
Oh, 0 to 9.5.
Yeah, 9.5 or 4.5. 9.5. Okay, great. So now, when you integrate this, you're gonna get y, right? Just a plain old y. So that means, and then you evaluate it from y equals x to y equals that. So that means it's gonna be negative x plus 9 minus x. Okay, so negative 2x plus 9 negative 2x squared plus 9x. I think I'm running out of space. Oh well. Negative 2x cubed over 3 plus 9x squared over 2. 0 to 9 halves. Plug in 9 halves. Huh. And then you're going to subtract, the lower limit's going to give you 0. So that goes away. So let's see here. Okay, so I get 243 over 8, which is the answer. Okay, so once again, right here, this is basically y equals x to y equals negative x plus 9 are the limits. And then these limits are x equals 0 to x equals 9 halves.